Evet arkadaşlar, herkese günaydın. Bugün örnek çözümler yapacağız. Internal forces'la alakalı. Good morning all. We are going to do some applications regarding the internal force diagrams that we learned last week. We talked about the theory of the internal forces, why we need all these internal forces last week, why we need, when we are doing structural design, we don't check only the internal forces on one point. We have to see the all internal force distribution in a diagram, and according to these diagrams, we select the most critical points and make our design. Design means we determine the dimensions of the structural members. Okay, so that's why we draw all these internal force diagrams. Let's get started to our examples here. Here is the first example. We have a simple beam here. Pin support, roller support on the beam in this part, uniform distributed load. We have 1 point load on the member. Hence, all these loads here, the 3 meter. We have 3 meter here, 1.5, 1.5. Total span here is 6. And magnitudes of the loads, here we have 4 ton as a point load, and we have 2 ton meter uniform distributed load. Here we're going to draw the and the M diagram. This is the question. Okay, when we have a structural system, what do we do first? Start the internal force diagrams. What should we do first? We have an idea. Maybe remember from the statics course, when we get a structural system, firstly we calculate the support reactions. Okay. We have to calculate the support reactions first. So we have a pin support here. Let's say this is point A. This is point B. We have here a vertical A, vertical support reaction. Also, since this is a pin support, there is a horizontal support reaction. Now, let's have a look to point B. Point B is a roller support. You know, this spacing in between triangle and this horizontal line means this is a roller support. So in this roller support, there will be only vertical support reaction. Okay, this is vertical B. Now, we have to calculate support reactions to start. Let's write the total X is 0. first. Total X in the horizontal direction. What we have HA, this one, HA, and any more loads? No, there is no any more loads on the structural system. That means HA equals 0. So there is no horizontal support reaction for this system, for this loading condition actually. Okay. If I change the load condition, there may be a horizontal support reaction. Okay. Now, we can do the vertical support reactions. So we have point A and point B. Let's do the total MB equals 0. Remember, for the pin and roller support, the moment is 0 on these supports. Okay. So we have a uniform distributed load. We have to convert it to concentrated load. How do we do that? We calculate the area of this uniform distributed load, which is 2 times 2 is the magnitude of this uniform, this part. Magnitude is 2, and the distance is 3 meters. So 2 times 3, let me write it here, 2 times 3 is 6 tons. 6 tons. Now, let's calculate the moment on the point B, total MB. We have VA. VA rotates the system in this direction. VA times 6 meters. I assume that the VA is in positive direction. So it's positive. Okay, we have 6. 6 times, this is the, by the way, this is the midpoint of the uniform distributed load. That means here 1.5 meter, 1.5 meter. Okay, so 6 times 4.5 meter, 4.5 meter. But is it positive or negative? If vertical A rotates the system in positive direction, in this direction, this one rotates in negative direction. That's why this is minus. They're in opposite directions. So we've just completed the uniform distributed load. Now we are going to do this point load, which is 4 times 1.5 to point B, 1.5. Is it positive or negative? It's negative because our positive direction assumption is this one at the beginning. So 4 tons rotates the system in negative direction. That's why I'm gonna put here a minus equals 0. So if we calculate the support reaction here, let me do. I have the result, but I need to check it. That's why I'm going to use my calculator. 6 times 4.5. Yes, 5.5. VA here, 5.5. So let me clear this part. And we write the load here. VA 5.5. HA equals 0. I'd like to put each load on the sketch. Now, this time, let's do the total MA. Actually, you know how to calculate support reaction. This is a just reminder for you. It's a kind of recap of the statics course, but you have to use this knowledge in this internal force diagrams. Total MA0. Now we have vertical B at point B. If we assume that this direction is positive, we can write all the moments according to this assumption. VA times 6 minus 4 times 4.5. And here we have 6 times 1.5 equals 0. Here, as you can see, I put minus and minus here. Why? If this direction is positive, all other forces rotate the system in negative direction. That's why I put these minuses over here. Vertical A. Oh, I'm sorry. I made a mistake. This should be vertical B. Vertical B. Because we are using this one. And also, vertical B. Okay. Now, we have just calculated the vertical B, which is 4.5. So let me write the force here. .5. Okay, we have the all loads on my structural system. By the way, let me give you this dotted line. Dotted line, you can remember, is the wave direction. Okay, we're gonna start to draw internal force diagrams, but before that, I'm gonna put here the sign convention of internal forces. All these are the positive directions. Okay. So this is P, M, M, N, N. Okay. So to start to draw the internal force diagrams, we need to know the internal. For example, by the way, question says us draw the axial force, shear force, and moment diagram. When we look at the structural system, there is no axial load. Okay, there is no axial load. That's why the axial load diagram will be like this. This is N, this is 0. That means there is nothing on the structural system. Now, let's do the shear force. To start the shear force diagram, we have to know the start point shear force. Okay, what is the shear force magnitude at the start point? If you get more experience, you can decide that by just looking at the structural system. But at the moment, we are going to start from the point A to point B in this direction. So if you can't decide what the first or start shear force, don't worry, you can do this. For example, I'm just looking for the shear force at this point. I can cut the system from here, from this point, which is so close to point A. So let me draw that point here. I'm gonna a little bit exaggerate. This is support, right? Okay, here. I cut the system so close to the point A. So I need the shear force at this point to start. So when I take a look at this system, I have to put the positive direction of the shear force that I'm looking for here. Take a look to top right corner. You can see the positive directions of the all internal forces. So which one I should use? This one or this one? You can see at the top there's a solid line. At the bottom there's a break line. Okay. If I bring it here, solid line, break line. So in my example, when I cut the system, you can see at the top I have solid line, at the bottom break line. So this side where I cut the beam is right side, according to this sketch. So I can put this direction here as positive direction. Give here first, and put here T. So there's a support reaction here. This is so close to this, the cut location is so close to point A. That's why there is no effect of uniform distributed load to this calculation. So if I write total Y equals 0 for this one, we are going to have T equals 5.5. So my start shear force is 5.5. Let's draw the curve. Okay, this is T. Remember, in shear force diagrams, top side is positive, bottom side is negative. It's same for the axial force, but the opposite is used for the moment diagrams. In moment diagrams, positive moment is shown at the bottom side. Okay, we are at point A now, and we have a shear force at this point, which is 5.5. Let me draw it here. Another color. Orange. 5.5. Connect this point to here. Okay. Where are we now? We are at this point. At this point. Here. Yeah, at this point. Now, from this point to end of uniform distributed load, there is no any other point load or anything else. There is only uniform distributed load here. Uniform distributed load. So let's say that point is here, end of the uniform distributed load. What we are going to do, if you take a look at our table we have drawn last week, there, what it says, if there is a uniform distributed load, shear force diagram is first degree curve. That means shear force diagram will be linear. Okay, we know that. And what we know more, if we know the shear force at one point, to go other point, we reduce the external forces from the first shear force. So what I have here, my start shear force is 5.5. Okay. Let's have a look at the uniform distributed load. The total magnitude of this uniform distributed load is here, 6. So what I'm gonna do, 5.5 minus 6 will give me the shear force at this point, which is the end of uniform distributed load. So what it is, 5.5 minus 6. Okay. So it's minus 0.5, negative 0.5. Gonna be here. 0.5. So I know this curve in between these 2 points will be linear according to the table that we learned last week. Okay, I'm gonna connect this one to here. Okay, this is linear. The top portion is positive. The bottom portion is negative. So this 0.5 is a negative value. But where are we now? We are at this point. Okay. Now we will go to the point load here. If there is no shear force or any loading on the member, shear force goes constant. It's like this till the point load location. So we are still in negative side. So we are now where? Here. We have a point load. We have to take into account the point load on our diagram. What was the rule? If there is a point load on the structural system, there will be a sudden change on the shear force diagram. This was the rule. Again, please take a look at that table. Okay, where am I? I'm at this point. My shear force value is at this point minus 0.5. So this is an external loading. We have to reduce this 4 tons from the shear force. So minus 0.4, sorry, minus 0.5. Here, minus 0.5 minus 4 will be the latest shear force at this point. So it will be minus, it will be minus 4.5, 4.5. I'm in the negative side. That's why I'm not gonna put here a minus sign, negative here. Because I'm at the bottom side. We know that side is the negative side. So I know what the shear force under this point load. After this shear force to the point B support, there is no load on the system. So the shear force diagram goes horizontally to this point. And this is closed here. Now we have just completed the shear force diagram of this structural system. This is T. Okay. Another, I will explain a few things more here. Now, let's look at some tricks on the T diagram. Let me change my color. For example, at start point, we have a support reaction, which is VA, right? VA, which is a support reaction. To start the calculations, we calculate the T. Instead, what we can do, if we know the shear force support reaction here, which is a point load, at this point, go up because you know our vertical A goes up. I'm at this 0 point and go up. Put here the point load there, which is 5.5. And after you draw all these things, at this location, you know, there is a point load here, which goes down and it has a 4 tons magnitude. Take a look here. I was here, which is minus 0.5. Put here the point load. Okay. And get this point. I'm putting these point loads to the shear force diagram with their directions on the structural system. You can see here, this vertical A is here. The 4-ton point load is here, as you can see. And at the end, what I have at point B, I have a 4.5 ton, which goes up. So put here the point load. What we have now, all the system closed. We start from this point. We goes up and okay, uniform distributed load. We head down to 0.5. After that, at the end, we close the system. That means we did correct. Okay. So kind of after you practice, after you do a few practice, you will see all these tricks. But if you are not sure about what is the start shear force, do this. It's a simple calculation. Okay. Simple calculation. Decide the start shear force and go ahead. Yes, let's draw the moment diagram. Shear force diagram. This was the shear force diagram. The moment diagram. So, to draw the moment diagram, we use the shear force diagram. Okay, shear force diagram. How we use that? Remember, we calculate the integral of the shear force diagram. That means we calculate the area under the shear force diagram and add these areas to the moment diagram. Okay, what is our start moment? This location is here. The point A. Point A is in support. You know, there is two support reactions, but there is no moment. Moment is 0 at this point. That's why my start moment value is 0. Start value is 0. So I'm going to start from this point. Okay. Firstly, I need to calculate this area. There is something missing here to calculate the area. Okay, I have the vertical edge 5.5, but what is this? What is this? We don't know this one. So we have to calculate it. How we are gonna calculate it? We will do it with using geometry. From the similar triangles, we can calculate this one. So let me write here. 5.5 over 0.5 equals x over, what is the total? 3. 3 minus x. This is the equation. If this is x, this part is 3 minus x, because the half of the uniform distributed load length is 3 meters. So we have this equation. If we do this equation here, let me see what it is here. It should be, yes, the x here is 2.75 meters. Okay. Here is 2.75 meters, according to this equation. If here is the 2.75, this portion will be 0.25 meters. We are not doing any strength of material calculation here. We are just doing geometry. Okay. Now we have dimensions to calculate the area. By the way, I must remind you something, which is, remember, if the shear force diagram goes from 0, at that point, there will be maximum moment value. So in this diagram, shear force diagram has a 0 value at this point. That means at this point, moment will be maximum. If I ask you, calculate the maximum moment, you will look for that moment at the 0 shear force point. Okay. Now, let's draw the curve now here. These are the critical points. Let's calculate the area. So, area of this shaded part, 5.5 times 5.5 times 2.75. Yes, 7.56. Here, moment here is 7.56. Okay, how I'm gonna connect this point to here? Our shear force diagram is first degree curve, linear curve, or a line, linear. So we increase 1 degree this shear force diagram. So this is gonna be second degree curve. So we're gonna connect these 2 points with a curve. In our sketch, we can't understand if it's second degree or third degree. That's why we generally write here, like this, second degree curve. Now we are at this point. Now let's calculate this area. So that area is 0.25 times 0.5. 0.06. 0.06. It's minus, by the way, it's minus. We are going to reduce that part and let's draw it. Okay, we reduce this area and we get this 7.5. Now, this is again second degree curve. Here we have this rectangle to calculate. Let's do it. This area is 0.5 times 1.5. Okay, 1.5. So this area is 0.75. So this is negative again. We are going to reduce it from this part. Over here. Uh, 7.5 minus 0.75 is 6.75. So how I'm going to connect these 2 points? The shear force diagram is horizontal. That's why moment will be first degree. That means linear. We're going to make a line in between these 2 points. Line means first degree. Okay, now we are at the end. If we calculate this area, 4.5 times 1.5. Area is 4.5 times 1.5 is 6.75. So this is negative area. We are at the moment 6.75. We are here at the moment minus 6.75. The moment at this point is 0. So how I'm going to connect these 2 points? Again, the shear force diagram is horizontal, so I have to connect these points to each other with a line. So I get this moment diagram. This diagram shows the moment distribution on the beam, under giving loading condition. Okay. So where we are, what is the last moment? Last moment here is 0. So what we have at that point, which is the point B, we have a roller support. On the roller support, moments are always 0. That's okay. We know that rule. So now we are moment 0 point. So we are doing correct. This is a self-check for you. Okay, you did all these calculations and you draw this moment diagram. If, for example, at the end, if you get a moment like this, here, a moment, somehow, that means you did something wrong anywhere else. Please go back and check your calculations, because we know that there is a roller support here, and on this roller support there will be moment 0 for simple beams. Don't forget this one. This is a self-check for you. Sometimes you make some mistakes while you are doing your calculations. You can press a wrong button on your calculator, so at the end you can get a wrong result. If you get this type of moment at the end, for example, for the roller support or pin support, that means you have to check your calculations one more time. Okay. This is a kind of self-check for you. Any questions so far, by the way? Clear or so complicated? At the beginning, it looks really complicated, but if you follow the rules, it's really simple, because you don't have to add anything to do that. You don't have to imagine something. There are some rules. If you apply all these rules, question, yes, it works for you. I have an example here. Okay, let's do this example. Okay, so second example. Yeah. Which is again yes. here I have also 3-tone. And on this point, back to uniform. My previous drawing was like uniform distributed dot. That's why I'd like to change it. Here, loading, which is
Hocam sesiniz gelmiyor.
Şimdi duyuyor musunuz?
Evet.
In my previous drawing, it was like not a uniform distributed dot. That's why I just wanted to redraw it. Because last year, I don't know, a few years ago, I drew a uniform distributed dot, but it was not shown like linear. One of our friends missed something in the course, during the course, and completely did wrong things in the exam. And at the end of the exam, he said, "Oh, you did these calculations for non-uniform distributed loads, whatever." So that's why I just wanted to emphasize this point is uniform distributed load here. This one. Here we have first one. Here, the next point we have this one, and here third one. Let's give the first one here. And one here. Okay. So here we have point A and B. Let's say here is A and here is B. Okay. Now, when we get the structural system, we are gonna calculate the support reactions. Okay. First, I think you know how to calculate it. That's why. By the way, let me do this point. This is spin support. This is roller support. Okay. So, the support reactions here. Vertical A. Here. Vertical B. And there's a horizontal A here. You're going to see there is no lateral loading on the structural system. That's why HA equals 0. So if you again make the total MB equals 0 and total MA equals 0, I'm not going to do it again because you know it. MA equals 0. From here, you will see vertical A is 3 ton. Okay, now we know the support reactions, but I'd like to add them to the structural system to see. As you can see here, the horizontal A is 0. Okay, I don't need to see this horizontal A here. What is the vertical A? It's 12. Right here. And what is vertical B? Here. 23. Now we have the structural system at the moment. We're going to draw the shear force and moment diagram because since there is no axial loading on the system, the axial force diagram is completely zero in this example again. So here we are going to draw the shear force and the moment diagram. We are going to start from the left hand side again. By the way, let me put the wheel direction. The dotted line is like this. Okay, here the dotted line is like this, and I'd like to draw here the positive directions to remind all these directions. Here. Here. P, and moment. Okay, these are the positive directions. Now, to draw the shear force diagram, we need to know the this first point shear force. Okay, we have to know it. You can see it directly, or if you can't do that, don't hesitate to cut the structural system from here. I'm gonna cut the system from so close to this point. Okay, I'm gonna cut it from here. It's so close. So let me draw a sketch for it. It's like this. Here at the end, what I have, 3 ton. Since this is so short number, uniform distributed loads doesn't have an effect. Actually, what I'm doing, if there's a system here, I'm cutting so close to this point load. Okay. To see what the start shear force here. Okay. I know this loading condition and which positive direction should I put here? Okay, you can see the top right corner. At the top, I have a solid line, as you can see, and at the bottom, I have a break line. So this point is, when I compare with the top right corner, is the right side. So I can put here this one as a positive direction. So in this loading system, if you write the total Y, the equilibrium equation, which is the total Y is 0. We're going to see 3 plus T, which are in the same direction, equals 0. T here is minus 3. No. So the shear force at the start point is minus 3. It's in the negative side. It's at the bottom side of our line. Okay, let's let's go ahead with negative value. This is the moment here. Next stage P. Okay, at the start point, what we have, this is the start point. I have -3. B. Okay, and here. Okay. Now, after this point, we are now here, as you can see. Now, from this point to support point, because at the support point, support is a point load for me. At that support point, we have a vertical point load which goes up. But in between this cantilever ends here and the support, there is a uniform distributed load. So let's take a look at this portion. We have a uniform distributed load in this part. What is the total magnitude of this portion? 1 meter times, by the way, I completely forgot to write the magnitude of uniform distributed load. It was the number 2 ton meter. Now, 1 meter times 2. 1 meter times 2, which is 2 at the end. Which gives us the total external loading here, which is 2. -3. Remember, this is minus. Our shear force is in negative direction at the bottom side. -2. That gives us -5. Okay, -5. How I will connect these 2 points? Since there is a uniform distributed load, I'm going to connect these points with a line. This is the first degree. Okay. By the way, change here. This is 5. Okay, I'm at the support point. So I'm here, the negative side. We have a support reaction here at this point. There is support reaction at this point. We are at -5, and there is a point load which goes up. What we did in the previous one, put here your point load with direction. Basically, we are -5 plus, which goes up 12, which is 7, positive 7. This is 7. Now I'm here. From here to here, till the point load portion, we have a uniform distributed load. So this goes down, That's why we are going to reduce it. What is the total magnitude for this orange portion? 2 times 2, which is 4, which is 4. 7 minus 4 is 3. Let's say 3 is here. How we are going to connect them? Since there is a uniform distributed load, here, this will be this first degree line. Okay, here the magnitude is 3. Remember, the top side is the positive side. Okay, positive side. Now, where are we? We are at this point. There is a point load there. If there's a point load, there is a sudden change, remember. What we did at the support reaction, we put here the load with its direction. That's why we go up. Here we have a 6 ton, and we will put here the 6 ton with direction. Total 6. So that means 3 minus 6 to get this point. That means again 3, but it's negative. It's negative. We are at the bottom side. So now we are at this point. We are gonna go to the point B. Point B. Here, there is a uniform distributed load portion. Let's calculate the total magnitude for that one. 2 times 2. Again, this is 4. 3 minus 3 minus 4, because it goes down. We're gonna go down. And the magnitude is here. It will be 7 minus 3 minus 4 equals minus 7. And we will connect this portion with a line since there is a uniform distributed load. This is first. Now we are at the support point. We are at the point point B. Point B. At the point B, we have point loads. First one is 12, which goes down, and the second one is 23, which is the support reaction, goes up. Can you see this? Here, this one, and this one. Here we have 2 point loads. So if we combine these point loads at the end, what we have? We have an 11, which goes up. Okay. Because the 12 and the 23 are in the opposite direction. The total point load is the kind of like this, 11. So I'm at this point now on my shear force diagram. So my resultant point load is 11. Let me add that 11 to this point. With the direction 11 minus 7 plus 11 is 4. I'm now at this point here. And I've just completed the point B. Now, where are we? We are at this portion. In between point B and the point load, which is photon, there is nothing. There is nothing. There is no vertical loading over here. That's why our curve for shear force diagram will go horizontal to the end of the beam. At the end, what I have a point load, which is photons, and again, which goes down. I'm here and put here the 4. What I get? 0 here. So that means the system is closed, not 0, but the system is closed. We come back to start level. So this is my shear force diagram. While I was drawing this curve, I used the point loads and their directions. And also there were some distributed loads on the system. The point load locations are critical locations because there's a sudden change on the shear force diagram. Take a look to all the blue lines on the system, on the shear force diagram. You can see there's a step up and or step down somewhere. There's a sudden change at this point. So we have just drawn the shear force diagram. Any questions so far here regarding this shear force diagram? If no, let's have a break. Then I'm gonna draw the moment diagram. Okay. I guess there's no question. Let's have a break, guys. We're gonna be here at 10:50. Okay, 10:50. Okay, see you. Okay. Now we have the shear force diagram. As you can see above here. Now we're going to do the moment diagram. But the question here, when we take a look at this shear force diagram, we can see there are 3 important locations. Let me show you. The first one is this: shear force 0, shear force 0, and shear force 0 point. So this means we are going to see maximum and minimum. Minimum means the absolute maximum value in the negative side. We are going to see the maximum or minimum moment values at these 3 points. Okay. So we will use the area calculation method. So our start point is here. On the structural system is here. So what is the start moment at this point? This is a kind of cantilever. The moment here is 0. Moment is 0. So we will start from 0. Now let's calculate the first area. The first area is this. There is a trapezoid section. So you can calculate the area easily. This is here is the 1 meter, 5 plus 3/2 times 1. So If you do that, the area is 4. Let me write it here again. 3 plus 5 over 2 times 1. So this value is yes, 4. Okay, this is 4. This point is 4. How I'm going to connect these 2 points? And take a look here. This is a linear. This is a line. So we're gonna increase the 1 degree above this shear force. By the way, I forgot something. Roll these points again. I forgot that. Okay, the area is 4, but it's -4. Okay, I forgot the sign. That's why, remember, for moments, the negative side is upper side. So that's why here I have 4, -4. So I will connect these 2 points each other with a curve. So this is going to be second degree. So here is minus. Now, the second area is here. Totally, the area, this area is 7 plus 3 over 2 times the distance here is 2. It's 10. The area is 10. It's positive. We are at the negative side. -4 plus 10, which is 6 at this point. Which is 6. Positive 6. So again, this is a line. We're going to connect these 2 points with a curve like this. This is the second degree curve, and this part is positive. Now, where are we? We are here. What we have here again? We have again a 10. There, these two residual sections similar to each other. That's why this is 10, but it's -10. We are at the positive side. 6 minus 10 is -4, -4. So here, connect these 2 points with a curve like this. This is 4. We are again at the negative side. Now, the last area is this. Four times 1 is 4. 4. So this is positive 4. We are at negative side. -4 plus 4 is 0. Yeah. We will connect these to each other with a line because we have a horizontal line here. We can connect these 2 points with a line, first degree curve. This part is negative, this is negative. Here, the bottom region is positive. Okay, let's have a look at the system. Here, we have 3 critical locations, and at these critical locations, you can see a minimum moments, which is the at the negative side and maximum moment here. So when the shear force diagram goes from 0, it's a critical location for my moment diagram. Okay. We should take into account these critical points. Now, what we have? Yes. Okay. Let's do this. Any question for this one? Next one. So we have a vertical column. Distances, we have yes, method, okay. Okay, we're gonna draw an M diagrams again. Here, I'd like to draw this sign convention here again. It's important for us. Okay. Okay. Let's do the first support reactions. It's good to have support reactions at the beginning as a rule, basic rule. Let me draw here. We will have a vertical. We'll have horizontal. We'll have a moment like this at this time. Let's calculate these loads first. Total horizontal, total x equals 0. Horizontal force 2 minus h equals 0. So here h equals 2 pounds. Total y in the vertical direction, what I have 3 minus v 0 equals total moment. Total moment. I can calculate 2 times bar load. 3 times 1. Distance direction minus 10 equals 0. Moment here is 10 plus 3, 13. Here we have a fixed support. That's why we have vertical, horizontal, and moment support reactions. We have 3 support reactions for this fixed support. Okay. Okay, we have all these support reactions. These are the support reactions. Okay. So let's draw the axial force diagram first. Axial force. This one. Now, axial force on this system, for example, I'm going to start from this point, on this point. Do I have an axial force? Yes, but what's the magnitude at the start point? I don't know at the moment. If I don't know, if I'm not sure about the internal force values, cut the system from here. Basically, when you cut the system, you will have this support, a small portion of loading, sorry, small portion of column, and this is the positive direction of the axial force. What I have more, the vertical support reaction here is what? 3 tons. If we calculate this axial force, actually you can see this is going to be 3 easily. But the common mistake here, if it's negative or positive, don't try to guess. This is what I suggest you. Instead, cut the system from here, so close to this point, and write this equation. N plus 3 equals 0. So N is minus 3, minus. You may say, okay, it's going to be 3. Yes, that's okay. It's going to be 3, but negative or positive? You have to decide. Okay, at my start point, is, as you can see, the view direction, dotted lines here. We can say here is 3, negative 3. So from this point to this point, the cantilever connection point, there is no axial load change. So till this point, it's going to be the same. Negative or positive? Negative. Because we have just calculated here. So put a minus sign over here. Okay, we are now here at the upper portion here. Is there an axial load? No. Take a look at the structural system here. There is no axial load here, which is 0. Let's have a look at the cantilever part here. Is there an axial load on this portion? No, there is no axial load here. And this is going to be 0. So this is the axial load diagram. There is only axial load on this portion, which is -3. Now, let's do the shear force diagram. Shear force diagram. Okay. Now, you can select the top point or bottom point. I generally start from bottom to up. We are at the bottom, so I need the support reaction, so shear force at the start point. By the way, to do that, we need to cut the system from the bottom support point as the previous one. If we do it, we have support direction, which is 2 tons. Okay, I have to put the positive direction of the shear force here, where I'm looking for the shear force. Okay, is this the right side or left side? What we are gonna do, again, take a look at top right one spot. As you can see, the solid line and break line here. If I put the solid and break line here, you can see solid line, break line. Okay, this side, according to my sign convention, is right side. So that's why I can put here the positive direction like this. While we are doing this, if you put here a wrong direction, you are gonna get a wrong sign. Sometimes you can get the wrong magnitude. Now we have T here. T minus 2 equals 0. T is 2 tons. So at this point, I have 2. Is it positive or negative? Take a look here. It's positive. Okay. You can see here the wave direction. That's why the left side is positive, right-hand side negative. Here we are at the positive side. When we come this point, until this point on this vertical column, there is no shear force change. At the top, there is a lateral load which goes right. So if you cut the system and take a look, its sign, it's going to be positive. So all the way down is 2. Positive or negative? That's okay. This, we have 3 tons here. When we convey to this 3-ton column, it's a kind of axial force for the column. It doesn't change the shear force on the column. So it doesn't have any shear force effect for the column. But let's have a look at this cantilever. Cantilever part is this part. you can see my structural member, and there is a force which is perpendicular to my structural member. That means this force makes a shear force on the beam, because my load, the external load, is perpendicular to my structural member. So we have to consider the shear force here. Now, what we will do, we are now at this point. Okay. Here, what is the shear force over there? I don't know the magnitude or direction. What I'm going to do, cut the system from here. Okay. Cut the system so close to this point load, but from here. Okay, let's draw it here. At this portion, I have 3. I cut the system from this point. So, is this left side or right side? Take a look to corner. Look at the break line is at the bottom, here at the bottom. Solid line at the top in our case. So this is the left side. So we are gonna use, this is the positive direction. So T is here, and this is the positive direction of T. T minus 3 equals 0. So T is 3 tons. T is 3 tons. So that means I will have a 3 here. So from the end of cantilever to the column point, there is no shear force change. There is no external loading. That's why there is no change on the shear force. That means it has a constant value, so it goes horizontal. Is it positive or negative? It's positive because of here positive. This is plus. What is this? This is the shear force. Okay. Okay. Now we're gonna do the moment diagram. Let me clear this part. I don't want to change the page. Moment. Hold it here. Now, we have, this is a cantilever system. We have a force at the top at this point. Here. We have another force here. Okay. Now what we'll do, let's calculate the moment of this force at this point. So force times distance, which is what? 3. I will have a moment of 3 at this point. So since by the way, calculate the area, or you can calculate the area here. 3 times 1 meter, 3. You can see here, it's positive. or negative. Ah. In cantilever, this one, if you connect these 2 points to each other, we have a rectangular triangular change. This is the cantilever moment negative. That means tension is occurs at the top. Then we have a horizontal force here. Let's first, this is a line. First, to calculate the moment at this point, what we have, 2 times 2 meters, 4. We'll have 4 here. So, change like this. Okay. And if we calculate the at this point, a little bit under this DMT column connection. Let's do it. What we cut the system from here. When I cut the system from this point, what I'm gonna get? This is 13 horizontal versus 2. What is the moment at this portion? This is the dotted line, the positive direction of the unknown moments here. Is this. This is the moment we are looking for this. Let's do it. And minus 13 minus 2 times 3 is 6. So they are in the same direction. So here pointing in the same direction, positive. This is negative T. Okay. It's gonna be minus 7. Okay, that point is here. Minus 7. So here, I will have a moment here. At the bottom, what I have, 13, which was according to these directions. So my curve will be like this. This point is 7, this point is 4. Here there is only 3, and here is 13. And all these are negative. Why? The system is a cantilever system. Okay. This is negative. This is the moment diagram. We have yes. I have a simple question. Let me see. Okay. Okay. Here we have a beam. The beam portion in the vertical direction. From distributed board. Which is 2 okay. Here we have one more board short one. And at the top of this vertical portion there is 2 distances. Equals to 1.5. Okay. Okay. Firstly, we're going to calculate the support reactions again. Point A and B. Here we have A, B, E. Here also HH. Okay. Let's try to total X equals 0 in this fractional system. Which forces are in the X direction? HA minus 2 so equals 0. HA equals 2. Oh. Now let's do the total MB equals 0. What I have here, where let's say this direction is positive. This one is positive. VA times 5 minus 4 times, we are at the point load 3. Now let's take a look this distributed load. 2 times 3 is 6. This is the total magnitude of this uniform distributed load. Where are we now? Minus 6 times 1.5. Okay. But let's go ahead to other side of the this point B. Here we have a horizontal load and with a distance. This rotates the system in the negative direction again. Minus 2 times 1.5 equals 0. Let me complete this one. Okay. Yes, vertical A here is 4.8. Oh, yes, there is the 4.8. This is 2. Okay, HA is 2. Vertical A is 4.8. If you do the total MA equals 0, we are going to get vertical B equals 5.2 pounds. You can do it by yourself. Now we have all the support reactions here. All support reactions here. Now let's draw the internal force diagrams. The first one is axial force diagram, and I have our structural system is like this. Now, what we have, what is the axial force at start point here, point A, at point A. There is an axial force, but we don't know if it's positive or negative. Let me check it. Okay, system. So the HA is like this. HA is 2 tons. But here, the positive direction of the axial force is always goes out, which is N plus 2 equals 0, and equals minus 2 tons. What? Minus 2. So, we can go to the minus side. So, if we take along the beam, there is no change. There is no horizontal external loading system. That's why this doesn't change. It goes constantly to the end of the beam. So in this portion, in this vertical cantilever portion, there's no axial load actually. Take a look at this part. There is no load in the axis of this number. That's why here is 0. This 2. This is the axial force diagram. Let's have a look to let's have a look to this shear force. Shear force. Okay, we are at this point. At this point. At the beginning, we are here. So take a look to point load, which is the support reaction. Put this loading over here with its direction. Let's do it. Blue. It goes up here. What is the magnitude? 4.8. This part is the positive direction. Okay. And now, from this point to this point, there is nothing. There is nothing. So, shear force diagram goes horizontal till this point. Now we are here. What we are going to do, there is a point load over there, which is 4, and it goes down. Put it over here. The magnitude here, this is 4.8 and minus 4. This point is 0.8. Okay. Now we are here. We are going to start to do this uniform distributed load here. Its magnitude is 6. We will go down. Goes down. We will do it 0.8 minus 0.8 minus 6. Over here, maybe. Minus 6 will be minus 5.2. 5.2. But this is a negative side. So since there is a uniform distributed load over here, I'm going to connect this point 0.8 to 5.2 with a line. Right here, first degree. So the bottom side is negative side. Now, Where am I? I'm at the this location. There's a point load over here. So where am I? I'm at minus 5.2. Let's put the point load here. Point load. Its magnitude is 5.2. So this is 5.2, but it goes up, goes up. So it goes to 0. It goes to 0. Shear force at this point is 0 anymore. Now, take a look at this portion. Is there any external loading over here to change the shear force? No. That's why we go constantly at 0, 0 level. Okay, 0 level. We are now here. We completed this lateral portion. Now we have the vertical portion of our beam, this one, this portion. Let's start this portion. Let's start this portion from this point. From this point, I'm here now. I'm here now. So there is a point load which goes left. Yes, we have to put it here. By the way, let me write the equation here firstly. After I have drawn it. If we are not sure if you are doing wrong or not, what is the start shear force at this point? Cut the system from this edge. Here I have to. I cut the system a little bit below this point. So I need to put here the positive direction of the unknown, which is here. Remember our sign convention. It was like this. The question is if this point is left or right. Take here our solid line and dotted line. Solid, it's same. But this point is when we look from left side. That's why it goes this side. Then we decide if it's left or right. Draw the arrow here and write the equation. 2 plus t equals 0. T is minus 2 ton. Minus 2 ton. Here, what is my shear force? It's minus 2. Right? The negative region 2. So from top of this vertical portion to the bottom, there is no any other external loading which change the shear force distribution on the beam or on the vertical member. So it will go constant. Here is 2. So this is the shear force diagram. This is the shear force diagram. Let's draw the moment diagram. Now calculate this area. Area is here. We have a rectangular area, 4.8 times 2 here is 2. The area is this. Let me draw. Value is 9.6. 9.6. Okay, if this is a constant horizontal line, this connection, this part is linear. Here is first degree. Now, by the way, let me show you this critical point. This critical point. Here there is a zero shear force. So please be careful with this point. And we need to calculate the first location of this maximum and max and magnitude. We need to calculate this area, this triangle. This triangle. So to do it, we don't know this portion. Okay, we don't know this distance. Firstly, we have to calculate this one. If we say here x, this total distance is 3 here. This portion is 3 minus x. And if we write the rule of similar triangles here, x over 3 minus x equals 0.8 over 5.2. Okay, 5.2. So if you do this equation, if you solve it, you're gonna get, check it, yes, x is here 0.4. Where is it? Here, 0.4 meter. So we can now calculate the area of this red triangle. 0.4 times 0.8 over 2. Okay. Over 2. It's 0.16. This is positive side. That's why we are going to add it here. 0.16. It's going to be 0.76. So this is linear first degree curve. That's why we are going to increase 1 degree up in moment diagram. This portion will be second degree curve. Here we have. Okay. Now, by the way, this part is positive. Now let's calculate the area of triangle. Now this distance is 3 minus 0.4 equals 2.6 meters. If you calculate this area, 5.2 times 2.6 over 2. Okay, let me check that area. 5.2 times 2.6 over 2. 6.76. So this is a negative area. The total minus 6.76. The result is going to be 3. point, we have 3. So how we connect these 2 points? Okay, again, we have line. We will connect these 2 points with a curve. Again, second degree curve. Now I'm at this point. From this point to the end of this beam, to this part, there is no area of shear force. That means it goes constant. Here we have 3. Yeah. And at the corner points, this is a kind of, check just a second. 3. We have the vertical member here. At this point, what we have is there a moment? No, if we cut the system from this point, because the force is here without any distance. But what is the moment at this corner? It's let me see the positive direction. There is no positive direction in the question, that's why I'm just taking that. 3. Okay, that's right. Cut if you are not sure, the moment at this point is 0. If you are looking for, there is no load over this column, cut the system from here and calculate the moment. So let's do it. I'm going to do it here. Cut system. We have 2 here, the positive moments. Here, moment minus 2 times 1.5 equals 0. So here, moment equals 3 ton meter. 3 ton meter. Okay, 3 ton meter. It's positive. I will draw it this side. We connect line. It's 3. And another trick here, if we have a corner like this, as the structural system, there's a corner here. The moment at each side of the corner equals to each other. Now we can check it. I calculated this moment from the here, and I calculated the other moment from this portion. So at the corner, if these values are equal to each other, yes, you are doing correct. There is no problem. Okay. This portion is moment portion. We have just drawn the positive moment diagram here. Okay, guys. Any questions so far? Actually, in next week, I'm gonna start a new subject. But what I suggest you, take a look at these examples, okay, by yourself. Try to solve it. If you solve these questions by yourself, you are gonna get experience about these questions, and maybe you will not need to cut the system at each point where you don't have the start point shear force or moment. If you do a few examples, yes, you can see what it is at the beginning without any calculation. But don't hesitate to do any calculation if you have any trouble. Instead of to guess what it is, I always recommend to cut the system where you want. Please try to do these examples. If you check in Google, you can see many YouTube videos regarding these internal force diagrams. If you write internal force diagram calculations to Google, again, you can find many examples to solve. Please do it by in the next stage. First, we will use these internal force diagrams. Okay. If there is a problem here, you can't go a step forward. That's why, please keep in your mind, try to do these examples by yourself. If you have any trouble, please let me know, send me an email. I will try to help you to explain subjects. Okay, thank you so much for today. See you next week. Take care of yourself. Have a good weekend. Bye-bye.